solve the initial value problem. Let's see if we survey this expression here. What do we got? 4 dg by dt plus 12g equals t. So the dg by dt gives it away that we're looking for an unknown function g in terms of t. So when we look at this, we say, oh, well, this kind of looks linear. There's only one g. There's a plus g, dg by dg by dt. I don't know why I'm tripping over my words here. Or you could write it as g prime. And then we've got this sort of our extra variable t over here. Okay, no problem. And we do have this initial condition g at 0 equals 1. We'll ignore that for now. That'll come in later. Because the way we handle an initial value problem is first you get the general solution, and then you use the initial conditions to get your particular solution. Okay. So we're just going to focus on 4 dg by dt plus 12g equals t for now. Copy this guy over here into our notes. And I will say, okay, g at 0 is 1. So we'll keep that off to the side. We'll keep it secret. We'll keep it safe. It'll be a surprise tool for later. Okay, so when I look at this, as I was saying, this does kind of seem linear. It is, but we do have to divide by 4 here. You need to not have a little constant there. So if we rearrange this, dividing everything by 4, not dy, it's dg. Old habits. So you get 3g and then 1/4 t. Okay. Now, if we were just after an integrating factor, which is our next step in the process, we don't really care what happens over here on the right-hand side. But since we're going to do a full solve, we do need to make sure that divide by 4 happened everywhere. Otherwise, that will throw off the formula that we like to use when solving linear differential equations. Okay, so we check. This is in standard form. Yep, we've got the derivative here all by itself. We've got plus, and we've got just the single g. Okay, that looks good. And in this case, our p of x, or I would call it p of t, is just this nice constant 3. And the integrating factor, maybe we'll call it I of t, is e to an antiderivative of 3. Well, that's not too hard to find. 3t, or 3t plus 1, or 3t minus 7, but why add in the constant? So e to the 3t, great. And then we have a formula. Now, you don't have to use the formula. You can do the longer process that shows that you know what you're talking about, multiplying by the integrating factor, reversing the product rule, and so forth. But since we're looking to solve this initial value problem as well, I want to jump to my answer as quick as possible. I will still sort of show off the formula, show my work a little bit. So maybe we'll write something like, hey, recall this nice little formula that the solution to our linear differential equation is the integral of what I would call q of t times the integrating factor. Actually, no harm in writing that. We got time, so we'll write the actual formula out to show things off, and then you divide by the integrating factor. Okay? So you take what's left over on this side. That's why it's so important that it's the 1/4 t. You would properly do the division there. Times the integrating factor. You integrate that, and then you divide again, or you divide by that integrating factor. It shows up again. So in this case, it'll be 1/4t e to the 3t. And I'm already starting to plan ahead as I write this out how I'm going to integrate this. And I can see it's probably going to be integration by parts. And we'll divide by e to the 3t. What we don't do is cancel these out. No, you got to go through the whole integration. So maybe we'll just grab a different color. And we'll say timeout. Let's just focus on this. And we'll come back to it later. All right? Good to stay organized like that. Yeah, if it's a short integration, yeah, just do it right in the formula. But if it's longer, requires a technique that requires a little bit of explanation, then yeah, no harm in saying, hey, pause. Let's just focus on this tiny little piece here. So definitely pulling out the 1/4, getting that constant out of there. And then, as I said, this is going to be an integration by parts, or IBP. Integration by parts, well, if you're going to do an integration by parts, you should say, what is your u, what's your v, what's your du, what's your dv? I'm going to let u be t. So du will be dt, and my dv will be, e to the 3t. And so my v will be e to the 3t over 3. Okay. Just doing a quick antiderivative there. If you need to, off on the side, do a substitution to get that, it's fine. Makes the question a little bit longer, but as long as you're being correct, and nothing wrong with that. So we've still got the 1/4 out front here. And then what is it? It's uv, so t e to the 3t over 3, minus the integral of v du. So that'll be e to the 3t dt over 3, except I'm going to bring that over 3 out here. And actually, I'm going to bring all the over 3's out and make it 12 out front. Okay. Now, we still have to finish up this integration, so we've got 1/12 t e to the 3t. What do the antiderivatives of e to the 3t look like? Well, good thing we've already solved that. E to the 3t over 3. Plus c. Always want to remember your plus c. You could say, well, we're not quite done the integration because I'm not done multiplying by the 1/12, so you want to leave the plus c over here. That's fine. Either way, you're going to get the same sort of expression. You'll just have a plus a constant. Okay. So we can multiply the 1/12 in, so t e to the 3t over 12 minus e to the 3t over 36 plus c. The plus c is important because we're not done the question, we're just done the integration, so we're going to come back here. We know what this is, and then we're going to come along and divide by e to the 3t. And then we will have the general solution. So 1/12 t e to the 3t, just writing it differently, minus 1/36 e to the 3t plus a constant, divide by e to the 3t. Now, if you find yourself making a mistake like this, and some people do, don't just come along and say, oh, yep, this cancels, this cancels, this cancels, because I've seen people do that sort of a thing, and it's a mistake. So if you find yourself doing that, go slow, treat this like a fraction. Let's go slow here. Split this up, right? If you have a plus b minus c over d, which is what we have here, actually, it's a minus b plus c, but it doesn't really matter. Okay, split it up into fractions before you start simplifying. Can save you some mistakes. So we got one of these over e to the 3t minus another one over e to the 3t, and then plus this c over e to the 3t. Now, there's nothing you can do to simplify this, but these ones, yeah, you can simplify them and cancel them out. But if you had just sort of rashly done it before, you would have had a plus c at the end rather than a plus c over e to the 3t. Or as I'm about to write it, c times e to the minus 3t. That's just because I like keeping everything all on one line if I can. So we're left with what still survives. T over 12 minus 1 over 36. And then plus c e to the minus 3t. So this is, as I said, this is our general solution. Great. But this is an initial value problem, so we need a particular solution. We want the one where g at 0 is 1. I'm even going to go back and double check that just to make sure. Yeah, g at 0 is 1. I was pretty sure, but it was so long ago I didn't want to just trust past me to have it right. So, okay, general solution. But now for some particular c, we will also get a function, a g function that has g at 0 is 1. So now let's solve for the particular solution. So we know 1 is g at 0, but we know g at 0 can be 1/12 times 0 minus 1/36 plus this c e to the minus 3 times 0. Just double checking. Yep. So that goes away. E to the minus 3 times 0, well, that's e to the 0. E to the 0 is 1. So really we have 1 is c minus 1/36. So just quickly rearranging, c has got to be 37/36, because then if I take 1 away, I'll have 36/36, which is just a really fancy way of writing 1. So now we've got our constant. We have the particular solution we want. 1/12 of a t minus 1/36 plus 37/36 e to the minus 3t. That is the unique function that solves this linear differential equation and also satisfies g at 0 is equal to 1.